All right, let's look at the orthogonal transformations. All right, so here's the definition. An orthogonal transformation is a linear transformation, right? So it has a corresponding matrix that preserves the lengths of a vector, right? So the distance from the origin will never change after the transformation, right? So which means that capital X comma capital Y would be the resulting point. So x squared plus y squared, you can put a square root if you really want the distance, but I'm gonna leave that out, has to be equal to the original point x comma y. So x squared plus y squared is the distance of the vector. So the resulting vector has the same length as the original vector, right? There's an interesting characterization of orthogonal matrices. Is that so you have a matrix corresponding to orthogonal transformation. If you look at the inverse of the matrix M, orthogonal matrix M, is exactly the same thing as the transpose. Right, so let's see if we can show that. All right, so let's say you have capital X comma capital Y, so that's the resulting point after a transformation, linear transformation. So I'm going to use A, B, C, D. Right, and apply to the original point x comma y, right? And we know that we know how to compute this. This is just going to be ax plus by and cx plus dy, right? So then we can just plug this. So this is capital X and this is capital Y. So plug that into that equation. We're going to get this. All right, so we have, let's see, capital X is ax plus by and squared. And capital Y is cx plus dy, then square that. All right, let's go ahead and simplify first. Let's see, so you have a squared x squared plus 2abxy. I'm just multiplying out. B squared y squared. And the second one is c squared x squared plus 2cdxy plus d squared y squared. All right, and collecting the like terms, so you have, let's see, there's an x squared term here and x squared term there. So we have a squared plus c squared x squared. So combine those together. And we have 2abxy and 2cdxy. So we're going to have 2 times ab plus cd xy. And then we have b squared y squared, d squared y squared. So we have b squared plus d squared y squared. All right. Then we know that this has to be equal to the right-hand side, which is x squared plus y squared. So this is equal to, maybe I'll put that, x squared plus y squared. All right. So by comparing the coefficients, we know that here, a squared plus c squared has to be equal to 1. And since there's no xy term on the right hand side, so ab plus cd equals 0. And then there's a 1 in front of y squared, so b squared plus d squared is equal to 1. All right, let's keep that in mind. All right, then, to show that M inverse is equal to the M transpose, we're trying to show, so let's try to show that if you multiply M transpose and M together, you're going to get the identity matrix. All right, so let's try that. So left-hand side let's see, M transpose. So this is M, right? Transpose is just A, B, C, D. All right. Original M is A, B, C, D. All right. So if you multiply it together, you're gonna get the, let's see, so you're gonna get the 4x4 matrix. All right. A squared plus C squared. All right. This times that gives you AB plus CD. All right, this times that gives you AB plus CD. This times that gives you B squared plus D squared. All right, then magically we know every single one of them. All right, so we know that A squared plus C squared is 1. We know that AB plus CD is 0, and that's the same thing. And B squared plus D squared is 1, which is the identity matrix, which is the right-hand side of the equation we are trying to establish. So this is already verified. So when you have a orthogonal matrix, which is the matrix corresponding to orthogonal transformation, then the matrix, the inverse of the orthogonal matrix is always the transpose of that matrix. So finding the inverse matrix of the orthogonal matrix is very, very simple. All you have to do is take the transpose. All right, that's it. I hope that this was clear.